Thank you. So I'm Peter Ondruska, and I'm a PhD student at Oxford University Mobile Robotics Group. And it's my pleasure to be here to tell you more about one interesting problem in electric vehicles energy management, where using state-of-the-art planning algorithms can make really difference. So when you buy an electric car, you will find out two things: that it has quite small battery, and it has this number, which is trying to tell you how many miles you can go until you run out of the battery. But the problem is this number is not very accurate, because the real range you can really make, it depends on where and how you are going. And some of the people, because this number quite jumps up and down, don't want to buy these cars because of this reason. So what we do, we don't show you the number, but we will show you a map. And that map is basically telling you where you can make it. And some of the people tried something similar before, but our algorithm is special that this map is specially customized for a particular driver and his particular driving style. And what's better, it's improving over the time. So as you are driving more and more, the map gets better and better and more tailored to your particular driving style. Except that we don't really need any other user interaction. The user just drives and it works. And we model the user behavior as stochastic planning process. And what's really good, all this is running at real-time speed. And that's really important because you want to get this implemented in real car. And we got a prototype of this method already implemented in real electric vehicle. All this is possible because at the end, I will show that generating of this map can be transformed to a problem of single Markov decision process policy evaluation. And I will show how it works, but before that, I need to talk a bit more about the problem and our model. So here, just to illustrate, here are 3 different drivers, and each one has different driving style. And for example, this first driver, he doesn't make it to this area because he really likes to drive along the highway. So he would like to go there along this highway here, and he would run out of the energy here. Whereas the second driver, he likes to travel through the city. So he's going to make it here because he would go this way. And we pick up this driving style, we learn it, and we show map which is specifically for you. So to give the overview how generation of such map works, so you have a map, and this is your position. So you consider a number of destinations where the driver could go, and you do analysis for each one. You predict and estimate how the driver would go there. So here is one destination and the likely route. Here is another destination, and we see like there are two likely routes, and it's good to consider both of them. And based on analysis of these routes, you can decide whether the destination is attainable or not. So you get what destinations are attainable, and then you show it to the user as a map. So when you are doing it like this, you need to solve 3 major difficulties or answer 3 major questions. So how to choose the set of the destinations? Like more is better, obviously. And we show we actually don't need to solve this problem because we at the end do prediction to every possible destination. And I will get more into it how it means later. So then how to estimate the routes to these destinations. And crucially, how to make all these running fast. So now I will explain, if you have your position and you want to decide about particular destination, how that calculation works. So, and as I said, we do this analysis for many, many, many destinations. So we have one destination, and we want to know whether it should be blue or white, whether it is attainable or not. So it's very simple. We say that the destination is attainable if the required energy to that destination is less than the energy we have in the battery. So we will be trying to compute this quantity here. So what we do, this quantity here, we consider it as an expectation over the possible trajectories, the distribution of the possible trajectories. So we are going through possible trajectories, and we weight them accordingly, the likelihood a driver will pick that particular one. And it's good to do it like this, like an expectation over the distribution, and not just consider like one trajectory. And we will see like this results in higher precision of the method. So now I will go through what the trajectory means and define these two quantities which are necessary for computation. So we look at the road network as one big state space, where the states are the road segments and the actions are the possible turns you can do at the end of each road segment. And now when we are looking at the car position and destination, there are two states. And we look at the behavior of the driver as kind of intent-based, that he's trying to get to the destination and on the way optimize some cost function. So this is one trajectory. Yeah, another. So now we will look into probability that user picks any particular trajectory. So as I said, we look at the behavior of the driver as kind of optimizing. So we store at each action a number, a reward. The driver receives when he drives through that edge. And we say that the driver will pick any particular trajectory with probability which is proportional to the exponentiated toll to reward. So here is an example. Like this is one trajectory, and this is what this probability is proportional to. So where do these numbers, these rewards, come from? So we are using machine learning approach to learn them. And we are using very simple linear regression, where we have, for each action, we have some features, and we learn particular weights for given driver, how much he likes, which expresses his reward in these features. And we learn this theta vector using inverse reinforcement learning, and we are using approach of Brian Siebert. So where these features come from, and what are they? So, and I forgot to mention, we learned that from the past trajectories user took in the past. So these features, we basically extract them from like OpenStreetMap map. Like they say, like what's the class of the road segment? If there is some stop or traffic light, and what if the driver went straight or he turned? We have features for that, and what's the speed limit? A few more. Like you can basically put anything you want there, and it will learn that automatically that parameter theta vector. So now get back and define this second thing, how much energy it takes to execute some trajectory. And it's equally simple. In addition to these rewards, we have stored at each edge a number which says how much energy it takes to execute that action. And simply, energy for one trajectory is just the sum over the executed actions. So here is an example for particular trajectory. And where we get these numbers from, how much energy it takes to execute particular action, we have basically two possibilities here. So we can use some physical model and simulate the behavior of the car, and what's the speed profile and what the driver will do. What we did in this paper, but what's actually better to do is we can learn this as well. So the driver is driving and is collecting data, and we can fit simple linear regression model to learn the consumption of the car automatically as well. And we have this published in another paper, which was published about 2 weeks ago. So please have a look if you are interested in details of this. So that was the model and how the computation should be carried. But if we do it like that, it wouldn't really work. Because in that equation, we had like sum over the possible trajectories, and we need to repeat the entire process for every destination. So that would really fast become computationally infeasible. So we need to do something smarter. So what we do is we transform the problem. And we transform the problem to Markov decision process. So remember, we said that the probability of particular trajectory is proportional to the exponential of total reward. But interestingly enough, the same behavior can be expressed as Markov decision process policy. When we say that the probability of user taking some action in any state is proportional to the sum of the masses of the trajectories which start with that action. Yeah? And one might ask, like, we didn't really help ourselves because this still requires summation through many trajectories. But actually, it turns out there is efficient dynamic programming in the algorithm which can compute this for us. So this won't be as much problem, actually. So as now, our network doesn't have rewards, but at each action, it has like probability, what the user will do at that state. And the probability of the trajectory is then simply just product of probabilities user will take these actions. So it's very simple. So now, if you look back to our quantity we want to compute and required energy from start to destination, we had it defined like this. And if we plug this now here, we find out that this computation is something already well known. And that's the evaluation of Markov decision process policy with respect to the energy functions. So we have the policy, like what the user will do at each state. And we have some function, energy it will take. So we can compute this using standard algorithm, and which has great property that is polynomial. So it can run very well. And as a small bonus, if you use any standard algorithm, you get not just policy from one point to the final destination, but you get the value of this policy for every starting point. That's what the standard algorithm gives you. That's great, but we actually want to do something else. We want to get the required energy from one starting point where the car is to many destinations, right? And we can get that almost for free. We will do something very simple. So we have our network here, and what we do is we just flip the orientation of the edges. Yeah? Very simple. But we keep everything else the same. So if there was some reward, we keep that reward on that edge as well. The same for energy. So now, when we look at any trajectory, so this was going from start to destination, the same trajectory can be traversed from destination to start. Moreover, because the rewards are the same, also the probability is the same. And the same holds for the energy required to traverse the trajectory. So to sum up, this was our original value. And we see that the required energy from start to destination is the same as the energy from destination to start in the transposed network. So again, so what's necessary just to do is we set the destination to the current car position, we transpose the road network, and we evaluate that policy. And that policy would give us for every starting point, which in these terms means every destination. So it was a very simple trick, and we did that to gain the efficiency. So that we don't have the sparse map where we just consider a few destinations, but we actually have very dense map where basically every state is considered as possible destination. So it's a very, very dense map. So that was the method and algorithmic details. And we also wanted to know how well that it does. So we did some quantitative evaluation. So we were interested how precise the map is as a function of how many trajectories you supply for training of the user driving style. And here we'll see more trajectories you supply to train the driving style of a particular driver, the prediction error of the map decreases. So that's very good. So this is the blue line. This red line was if we just consider to every destination just single most likely route, yeah? Because we are considering the entire distribution of the routes, not just single one. So it really helps to do it. And we also see it performs quite better than if we just consider like basic preferences, like user will always choose the shortest path or fastest path. So in these cases, we are able to decrease the prediction error by like 30%, from 9 to 6. So the other properties of our method is that running time is something n to the 1.5, where the n is the number of states. And our implementation is able to do the execution of the prediction in like 5 seconds. So every 5 seconds, you get a new map. So that's sufficient for real time because the car doesn't really move so fast that it will change state so fast. And that map has about 1 million states. So it's quite good. And what's actually quite nice as well, that the entire code has like 200 lines of MATLAB code. So to implement this, it's very simple. You can do that in like 2-3 hours. So to conclude, I presented a method to show a drivability map as opposite to show one number, which has many disadvantages. And we faced 3 challenges: how to choose the set of the destinations, and we resolved that we actually don't need to solve this because we do the prediction for every destination on the map. Then we needed to solve how to estimate the route to each destination, and we do that by first learning the driver preferences from past trajectories, and then do the prediction. And how to make it fast? We employed 2 tricks. We transformed the problem to Markov decision process policy evaluation, and we also used the road network transposition. So that was all from my side, and thank you for your attention, and now I'm ready to take some questions.
Can you go back to the beginning where you have this inequality between the expected energy to go less than or equal to the available energy?
Yes, I'm trying to get there.
Yes.
Yes.
So I wonder if, why you're using that inequality, wouldn't it be better to bound the probability that the energy you're going to spend from start to destination is less than or equal to the available energy? So you want to bound the probability of the inequality.
Yes. Very good question. Very good
and
question.
Then you can bound, using the Markov bound, you can...
Yes, very good question. We solved that a bit differently. In this other paper I referenced during that energy slide, what we did, we extended this approach. I will just go there. Yeah, in this paper, we didn't just learn the energy as using machine learning, but what we also did, we extended this such that you can ask the question like, show me just the destinations where I have 90% confidence I will make it, or any probability confidence bound you want. So go and have a look here how it works. It's I think very nice extension, and we did that by just extending this method here.
Using the Markov bound, you will bound
yes,
that probability
you
automatically, right?
Yeah, because what we do here, as we have this equation here, that's basically a mean of this distribution, right? What we did in our extending paper, we also recreated the distribution to some moment, and then we could set that probability bound, like the mass, how much mass of this distribution should be less than our available energy. So then we get that confidence bound you are probably seeking for. Yeah, feel free to ask me later for the details.
First of all, congratulations for the work. Just a quick question. I was just wondering, I mean, usually when you hop on a car,
yes.
Usually you have a destination in mind. Not in terms of, I mean, you don't really care about all the possible places that you want to go. You usually have one destination in mind. And when you mention, you know, those different maps for different drivers, and then you said, oh, the same car, the same position, cannot reach this destination because the driver will want to take a highway. But what if the system said, well, if you want to make to this place, you cannot take. So instead of like assuming what the driver is going to do, why can the system advise the driver?
Yeah, I got the question. Yes, that's interesting. That's a really interesting question, and because when the driver is going to make it somewhere where the map is showing, like based on your usual driving style, you will not make it. The driver will probably change its behavior, right? So right now, our method cannot find out that the driver changed the behavior. But it's interesting question. It's like, I will just show a map, and so for example, if the driver was going here, and he knows if he changes his behavior, he will make it, the real range is longer, right? And interestingly, there is also the opposite side of this problem. If he was going here, he would probably drive really aggressively because he would be confident, and the real range would be shorter. So these are interesting problems. You want to probably show the range, which is kind of responds well to his behavior afterwards. He sees it. So it could be say like this method works well until the driver doesn't look at it, because then he changed the behavior, and yeah. So that are interesting extensions.
So one last question.
Yes, I believe that for the same driver and the same trajectory, your energy requirement may depend on a number of state variables that are not easily observable, such as the load of the car, the wind, the temperature, the traffic,
yes.
and other conditions, air conditioning or heating
yes,
in the car.
Yes.
So how does this affect the precision of your estimates?
As we had it here, it would mean these numbers are different, right? Yeah. This how much energy is required. And what we did also in that extending paper, we learned these numbers for these particular situations. So for example, if the driver turns on the air conditioning, these numbers get automatically replaced for that situation. So if we do it like that, as soon as you turn on the air conditioning, these numbers get updated, and the new map is shown.
In this case, it is observable. My question is with respect to
some
that are partially observable.
My answer to that, it's really hard to deal with these kind of things. But what you can do, you have some features for every action, and one of your features might be like it's one if it is like Monday morning, right? And then the model learns that on Monday morning the energy consumption is higher. So it can deal with that in this way.
Yeah,
So.
let's take the discussion offline and move to the last topic.
Thank you.